Welcome to our discussion on functions. Okay, what is a function? Well, I like to tell my students one example of a function is a meat grinder. Now, stick with me. I know you're thinking, what? If I take some beef and I stick beef in a meat grinder and I turn the handle, it's going to spit out hamburger, right? If I put pork in the meat grinder and turn the handle, it's going to spit out sausage. If I take as hoof and snout and stick it in there and turn the handle, it's gonna give me turn the crank, it's gonna give me a hot dog. But if I go back and put beef in it again and turn the crank, it's not going to give me something different than the first time. It's going to give me hamburger again. And that's basically a function. I can get the same thing for different inputs, but I can't get different things for the same, I can't get different outputs for the same input. So every time I put an input in, I have to get one and only one output for that. And it just depends on what the inputs and outputs are, right? The different functions have different inputs and different outputs. But you can also think of it as a question and answer machine, right? Where the question is the input and the output is the answer. Well, you can have the same answer for multiple questions. Is the sky blue? Yes. Is grass green? Yes. Can birds fly? Yes. Well, of course, there's some birds that can't, and grass can be dead and not green, but you get the idea, right? But you can't then come back and go, is the sky blue? And it's going to say no. The idea is you can get the same answer over and over and over again for different questions, but you can't get different answers for the same question. That's what defines a function. Here are some simple examples. If we let senators be the input and states be the output, then that is a function because every time you give the machine a senator's name, it's going to spit out the state that they are a senator for. And there's only one answer. You can't be a senator for multiple states at the same time. This is a point in time. They could obviously switch at some point, become a senator for a different state down the road somewhere else. But you get the idea. At that point in time, it's only one answer. But if we switch it around and put states in as the input, now it's no longer a function because if you put in the state of Mississippi, it's going to spit out one name, and then you put in the state of Mississippi, it's going to spit out a different name because there's two senators for Mississippi. In fact, there's two senators for every state. So any state that you give it, it's going to kind of be like, well, okay, now I don't know what to do. Do I give you this name or this name, right? Or anytime you can have two answers, it's no longer a function. If you went with people and birthdays, same thing happens. If people is the input, then you're only going to have one output because we all only have one birthday. But if you switch it around and put birthdays in, the answer you get out is going to be hundreds of thousands of people because there's hundreds of thousands of people born on every particular day. Unless you give the year, then instead of hundreds of thousands, it's still going to be lots, right? There's lots of people born every single day. So even if you include the year, it's still not going to be a function. All right, what about Social Security numbers? Well, if you put in Social Security number in, since everybody has a unique one, then there's only one person tied to that, and that's going to be good. That's going to be a function. What if you switch it around and put the U.S. citizen in and then ask for the Social Security number? That's also going to be a function. That's going to work because those two variables, Social Security numbers and U.S. citizens, comprise a one-to-one function. That is something where every one input is mapped to exactly one output. So you no longer get multiple inputs going to the same output, right? It's no longer the sky is blue is yes, and the grass is green, it also goes to yes. It's every time you ask it a question, you get a unique answer, and that's called a one-to-one function. And those are the only functions that have inverses, something that we'll learn later. But that's good to know because it has to be one-to-one to give us an inverse. Okay, quickly, domain and range. Domain are all the things that we're allowed to plug into a function, and range are all the answers, possible answers that we can get out of the function. So for instance, if we were doing, people and birthdays, the domain would be all people. We could plug any person in, and the range we would get would be all 366 days of the year if we were just doing that, and then of course all dates going all through time if we were allowing for years, right? But if we were just saying birth date as far as you were born March 7th or you were born April 3rd, that type of thing, there'd be 366 possible outputs because of the leap day, right? February 29th. And then our domain, like I said, would be all people. Something that wouldn't be in our domain would be like, a dog or a chair or a house, right? Anything that wasn't a person, because you can't put that in and get a birthday. I mean, technically, a dog has a birthday, but not in this function. A house doesn't really have a birthday, right? A book, a chair, they don't really have birthdays, so those wouldn't work as well. So you get the idea. The domain is everything we're allowed to plug in, and the range is everything we can get out of the function. Now, when we start doing these things with algebra and actual numbers, instead of these silly examples of peoples and birthdays, the input are just all numbers that we're allowed to plug into the function. And for most functions, we can plug any darn number we want into it. But there are a couple specific functions, families of functions, that we can't plug things into. Like, for instance, square roots. We can't put negatives into square roots, so those would be taken out of the domain. And we can't divide by 0. So if our function had any variables in the bottom of a fraction, we'd have to make sure that anything that made that thing equal to 0 was also taken out of the domain, because that would make it an invalid operation. Okay, so that's what's going to happen when we get to more complicated things. We've already been talking about these things as variables. These are the unknowns, the things that can take on multiple variables, multiple values, I should say. The independent variable is the question, that's the input, and the dependent variable is the answer, that's the output. We normally let X be the input and Y be the output. Those are not hard, fast rules. They don't have to be that way. That's just what happens more often than not. So don't feel like you always have to use those letters, but more often than not, those are the letters that are used. We also don't always call them independent and dependent. These are normally only reserved for experiments, things where you can actually manipulate the independent variable. Otherwise, if you're just having data that you collected that you can't manipulate, then we normally call it the predictor and the response. So the predictors are the inputs, the response are the outputs. Semantics, just in case you go on to a stats class, you might hear those phrases as well. It means the same thing, input and output. The reason why it's the dependent variable is because the answer you get always depends on the question you ask. Okay, let's look at some financial versions of these things. Some quick vocabulary word. Payments, obviously the amount of money you have to pay back on a loan. Principals, the total amount of money that you borrow for a loan. And the APR, or the annual percentage rate, is the percent of the interest on the loan. And it's not how much you actually pay, it's how much is actually sold to you. You'll see how it's different. The APR is what they state is the annual percentage rate of the loan, and that would be only if you were paying back the lump sum all at once and compounding the interest all at once. But we all know that never happens because of compound interest happening, daily and monthly and things like that. The actual amount of interest you pay will be different, and we'll see in a second what that's called. Okay, so for this simple example, we're going to borrow 1,000. That's our principal. The APR is going to be 12%. We're going to have the interest compounded monthly, so that's the period. So the periodic rate is always the APR divided by the number of periods in a year, so 12% divided by 12, and our periodic rate is going to be 1%. If we were paying, or if it was compounded weekly, right, this would be 52. We'd have 12% divided by 52. If it was daily, it would be 365. If it was quarterly, it would be 4, right? So you get the idea. Now, if we set up our Excel spreadsheet with all this information, we can now start to figure out how much we pay each month, right? So we can see that we have a starting balance of $1,000. Here's our starting principal. Our interest is 12%. It's monthly, so there's 12 in a year. And then this periodic rate, I didn't just type in 1%. I defined it as G2 divided by G5, because that way, if we want to change it up, the numbers will change with us, right? So instead of having 12%, maybe we want, instead of monthly, maybe we want to do it quarterly, right? Or maybe we want to do it daily. And if it's daily, well, then we can't see anything, so we have to come up here. We have to increase the decimals until we can actually see it. Oh, okay, that's what it is. All right, but if we're going to put this back to monthly, we don't need all those decimals, so we can shrink them back down and go, all right, that's 1%. Same thing here. Rather than just typing in 1,000, why don't we define that as our principal? So we're just going to say equals that cell. Click on it. So it's now going to equal G1. So now if I want to borrow, $200, it changes. Or 20,000 or 200,000, it changes. Obviously, I can't see that now, so I got to come over here, and if I double click on that, it makes this wide enough to show whatever the biggest thing is in that column. But I don't need 200,000, I just need 1,000. And if I do this, it'll shrink it back again. All right, so anytime you want to quickly format the columns to match the width of the largest thing there, just put it up in between until it turns into that symbol and double click. All right, interest is just our balance times the periodic rate, but we don't want to do 1,000 times 1%. We want to leave it dynamic, so in case this changes, so we're going to let it equal this cell times, and it's always asterisk, this cell, and there's our interest. And then our new balance is just going to be the sum of those two. If you go over here and click the auto sum button, it automatically sums up. But you see how it sums up everything? It sums up anything that looks like a number, and we don't want that. So instead, you can drag this so that it only gets those two cells. Or you can type it in by hand, right? If you go up here, you can always just type in what you want. I want it to start in the A column and see that's all of them, or I can come back and make it start in the B column, B4 to C4. So you can change it whichever way you like. Okay, so there's one row down. Now, the next month, this starting balance is going to equal what it finished off in the last month. And again, we don't want to just type that number in. Let's define it. It's going to equal that amount. And then we could go through the whole thing of typing in this formula and this formula and doing that over and over again. But the nice thing about Excel is if you drag and drop, it will copy that formula. So this initial formula was B4 times G6. This one's now B5 times G7. So you see how it moves down, it moves everything down because it's not smart enough to know that you wanted this times this, and then it wants this one times that same number. It does it all based on position. When I'm doing the formula for this cell, it says take the cell that's exactly next to me, right on my left, and then multiply it by the cell that is over by 4 and down by 2. So that's where we get those two cells. When we move to here, it does the one that's to the left, and then over and down, and you see that now it's down too far. And then this one, if we go here, oh, sorry, I just reformatted that one. If I go here and click up here to see where it goes, you see that it's down by 2. And so on and so forth. That'll always be the problem. So what you need to do is tell Excel to hold G6 in place. We can let the B4 thing change with every row. We can let it go down to 5, 6, 7. But we need G6 to stay the same. So just put a $sign in front of the 6, and what that does is it holds it at 6. It won't go down anymore. So now when you drag it down, the next one is also G6, and G6, and G6, and G6. Now that holds the 6 in place. If we wanted to hold the G in place, because if I now took, let's say I took this function and I drug it this way. Well, remember, it's the thing to the left, and it's over 1, 2, 3, 4, and then held at 6, right? So this one went to H, but held at 6. And if I drag it over here one more, just to see what it is, right? This one you can see it's the one to the left, and now it's over at I, but it's held at 6. So you see it doesn't hold the columns, it doesn't keep G constant, it just keeps the 6 constant. If we wanted everything to be constant, right, both the G and the 6, all you got to do is put that in front of the G as well. And now when I pull them over, see, it goes to the one to the left, but it stays on G6. And then this one is the one to the left, but stays on G6. So it's just a quick, easy way of holding pieces of your function constant whenever you need them, because when you drag and drop, it'll always move based on position. So let's go back. We don't need we don't need the one in front of here. But it's okay if it's there, right? It's okay if it's one way or the other, but I don't like to put things in I don't need. So I'm just gonna leave it as the dollar sign in front of the 6 only. Okay, and then this one is just like that one. It's summing up those two things. So we can just drag that one down the way it is, and you can see that it's summing up those two numbers. Okay, now that we have this whole row defined correctly, right? It's no longer, this one was defined by that number way over there, but this one is defined there, and we know that this one needs to have the same relationship. It needs to be defined by the cell that is up 1 and over 2. So if we drag this one down, it's going to do what we need it to do. And if we drag this one down, which we already did, it's going to do what it needs to do. And same thing with that. And rather than doing all 3 individually, we can do them all at the same time. And it populates everything for us. Again, one of the nice things about Excel is it knows how to do these things. Okay, so now you can see that at the end of 12 months, this is how much money you would owe. And you can also see that that is not exactly 12% of 1,000, right? If we just do the math really easily, equals 1,000 times 0.12 times 12%, you can see it's $120. Should have been 120. We got this extra amount, this $6.83, and that comes from the compounding, the month-by-month compounding. This is what we actually pay, so that ends up making our APY, our annual percent yield. And annual percent yield is very simply a ratio, and it's a percent change. It's how much money it changed by, right? It went up by $126.83 divided by where it started, so difference over original. So 126.83, that's the difference in we started at 1,000, ended at 1126.83. Difference over our starting point over our 1,000. Do the math, that gives us 12.683. Obviously a typo over here. So 12.683 is our annual percent yield. That's the effective interest rate that we pay for this money. So in effect, when this actually happens over 12 months, we actually end up paying 12.683% instead of just a flat 12%. And that's it for chapter 1.1.